This month's CE is on evidence-based practices for strategic and tactical firefighting. Learning outcomes. To provide information and resources based on recent research focusing on modern fire behavior, building construction, and fireground strategy and tactics. Jones and Bartlett Learning developed this publication to inform the fire service on research coming out of UL and NIST. It is the hope of Jones and Bartlett Publishing that this will help save lives. This training is ideal for enhancing training from the Firefighter 1 and 2, fire science degrees, and fire officer development programs. This is an exciting time to be a firefighter. Today we are experiencing major changes in our understanding of basic fire behavior and the tactics used to attack fire. If we do not understand the impact of these changes, we may put ourselves in positions that are so unsafe that they prevent us from accomplishing our mission of preserving life and property. Changes are occurring in building construction and construction techniques used to construct today's buildings. Household furnishings and other building components are increasingly constructed from petroleum-based materials. Today's fires release energy faster, reach flashover potential much sooner, and may reach higher temperatures and are much more likely to become ventilation limited than the building fires even a few years ago. Because of these differences, it is important that our techniques for ventilating, applying water, performing rescue reflect the changes in our modern building construction. Historically, the principal means of developing firefighting strategy and tactics has been based on the observation and experiences of firefighters. These observations and experiences provide us with valuable tools to more effectively fight fire. Yet, experience-based techniques do not provide us with the means to fully measure and understand the actual progression of fire and the impact of each action we take at the fire scene. Because of these limits, we sometimes draw inaccurate conclusions. These conclusions have sometimes resulted in ineffective and counterproductive courses of action. New research helps us further understand the actual progression of fire and the impact of each action, and research has been based on live fire experiments in laboratories and acquired structure. National Institute of Standards and Technology, NIST. This group enables advances in firefighter safety, fireground operations, and effectiveness of fire service, develops and applies technology, measurements, and standards, and improves the understanding of fire behavior, prevention, and control of fires to enhance firefighting operations, fire equipment, fire suppression, fire investigations, and disaster response. For more information about NIST, you can access it through the link below. Underwriters Laboratories, UL. UL's Fire Safety Research Institute is dedicated to increasing firefighter knowledge to reduce injuries and deaths in the fire service and in the communities they serve. UL Experiments and Reports. UL has conducted a number of experiments and produced reports on those items. These include comparisons of modern and legacy home furnishings, effectiveness of fire service vertical ventilation and suppression tactics, firefighter exposure to smoke particulates, firefighter safety in photovoltaic systems, Governor's Island experiments, impact of ventilation on fire behavior in legacy and contemporary residential construction, improving fire safety by understanding the fire performance of engineered floor systems, structural stability of engineered lumber in fire conditions, study of residential attic fire mitigation tactics and exterior fire spread hazards, and fire service positive pressure ventilation during fire attack in single-family dwellings. New firefighting vocabulary and terminology. Flow path. The volume of air or hot gases, smoke, and small particles between an inlet and an outlet that allows the movement of heat and smoke from the higher pressure within the fire area toward the lower pressure areas accessible through doorways, window openings, and roof openings. Vent point ignition. A pre-flashover condition that exists when the superheated unburned particles of combustion ignite around a ventilation opening. The smoke and gases have already reached their ignition temperature and are too rich to ignite until the proper oxygen-to-gas ratio is achieved. Bi-directional flow path. A two-directional flow path through a horizontal opening which allows the hot smoke and gases to exit through the top half of the opening while allowing cool, oxygen-rich air to entrain to the seat of the fire at the bottom of the opening. Ventilation limited fire. A fire in an enclosed building that is restricted because there is insufficient oxygen available for the fire to burn as rapidly as it would with an unlimited supply of oxygen. Increasing the supply of oxygen to a ventilation-limited fire may result in a ventilation-induced flashover. Fuel-limited fire. A fire where the elements of the fire tetrahedron come together in a perfect balance to support the combustion process. The only element that is limiting the growth of the fire is the amount of fuel that is available to burn. Vent, enter, isolate, search. A method of search for fire victims that consists of ventilating an enclosed space, such as a bedroom, entering the room, closing the door to isolate the room from the fire, then quickly searching for any possible victims. Transitional attack. An aggressive offensive exterior fire attack that occurs just prior to entry, search, and tactical ventilation. Also referred to as an offensive exterior attack, softening the target, a blitz attack, or resetting the fire. Heat release rate is the rate at which fire releases energy. This is commonly referred to as power and is measured in watts or joules per second. Fire behavior. With an improved understanding of fire behavior, the importance of controlling ventilation is a key factor to safe and effective operations. Safer and more effective methods for conducting search operations have emerged, and firefighter safety and survival are improved through quicker suppression techniques. Flashovers. Increased incidents of violent and rapid flashovers are being encountered in residential fires. UL and NIST studies have been conducted to provide knowledge and tools to better understand this phenomenon. Testing has included full-scale burns in both laboratory and acquired structures. UL and NIST experiments include component testing of modern furnishings, furnished room experiments, full-scale house burns in the laboratory, and full-scale burns in acquired structure. The evidence-based research points to topics that the fire service needs to have a better understanding of in order to operate safely in today's fire environment. This includes the topics of fire dynamics, ventilation and fire flow paths, how fire spreads, applying water in coordinated fire attacks, rescue and safety considerations, and basement fires. This slide shows the comparison of the fire growth curve. On the left, you will see the traditional fire growth curve represented by a fuel-limited fire. You will have ignition, growth, a fully developed fire, then you will ultimately enter the decay stage. Again, the only thing limiting the growth of this fire is the amount of fuel that's available to burn. However, on the right, you see the comparison with the ventilation-limited fire growth curve. You have a similar ignition, a similar growth, but you will go through an early decay stage due to a lack of oxygen. At some point, there becomes a change in the ventilation profile, which allows oxygen to re-enter the structure, followed by a rapid growth phase to a fully developed fire, and then ultimately down to a decayed state again. Both NIST and UL have conducted a number of experiments comparing the legacy versus modern fueled and built environments. The changes to building materials and the changes to fuels inside have created dramatic changes on the fire ground that we're experiencing today. Some important points to remember regarding fire dynamics are that the stages of fire development change when fire becomes ventilation limited. It is common with today's fire environment to have a decay period prior to flashover, which emphasizes the importance of ventilation and its timing. The absence of visible smoke means nothing. A common event noted during the experiments was that once the fire became ventilation limited, the smoke being forced out of the gaps of the house greatly diminished or stopped altogether. No smoke showing during the size-up should increase awareness of the potential conditions inside. Structural collapse should always be considered in your size-up. All residential floors can collapse in your operational time frame, especially with an unprotected engineered floor system. Modern construction concerns. Higher performing insulating materials and lighter weight materials change the way fire burns. Solid dimensional lumber has been replaced with lower mass materials and manufactured structural components. Furniture constructed of materials derived from petroleum products are found in every room of a modern home. Heat release rate increases as fires burn hotter and faster, and the methods of heat transfer in a tightly sealed house have resulted in rapid fire spread. As a result of the changes on the modern fire ground, we have seen changes in our operational timelines. When you deal with the legacy fire, you were often 10, 20, 30 minutes in the event was the shortest possible time that you had to flash over, while flashover would occur at the longest around 35 minutes. Time to collapse with unprotected floors would go as long as 45, even close to 50 minutes, while the time to collapse protected floors would greatly exceed an hour. When in comparison with today's fire ground and the modern timelines, you can see flashovers are occurring in 3 to 4 minutes. The longest time to flashover is approximately 5 minutes. The time to collapse with unprotected floor systems is roughly 10 to 12 minutes. And collapse time for protected system isn't exceeding the 30-minute time frame. So what we have is an accelerated fire growth curve that's having a tremendous impact on our operational timelines, which means we need to keep these in the back of our head while we're mitigating the hazards on the fire ground. Modern versus legacy timelines. NIST and UL have conducted fire experiments comparing the growth of fire in a room with synthetic furnishings versus rooms with older contents. In these experiments, a room with legacy furnishings took longer time to flash over or oftentimes did not reach flashover, while a room with synthetic furnishings, however, flashed in a very short period of time. In other words, a room with furnishings produced from natural materials burns much slower than a room furnished with synthetic or plastic-based materials. Perhaps the greatest value of these experiments is their ability to show that fires fueled by synthetic furnishings contain much greater fuel load, progress faster, and flash over more quickly. This creates much more dangerous conditions for both occupants and firefighters. Flashover comparison. Comparison of room furnishings for a legacy room and modern room fire. UL conducted a study with a 10 by 10 room with an 8 by 8 opening of both legacy and modern fueled rooms. The legacy room on the left was filled with products of cellulose material, natural wood, cotton fibers, wool products, while the modern room on the right was filled with your synthetic materials that are petroleum-based products. The legacy room with the older furnishings has little flame showing at 3 minutes and 25 seconds after ignition, while the modern room furnished with petroleum-based products has flashed over in the same period of time. Now when we look at it all together and see all the different factors that have changed the way fires burn in modern homes, we see that we have created a much larger house with much more open concept living and open spaces, taking out the compartmentalization that was really a true friend to the fire service. We've got evolving fuel loads that have changed from the natural cellulose-based materials to more synthetic petroleum-based products. We have increased void spaces through engineering construction. We've got change in our building materials going from mass to more lightweight construction. We're taking these larger homes and we're putting them on much smaller lots, and we're adding new technologies every day that has really created the perfect storm for the firefighters and the fire service. And what you see time and time again on the fire ground is a much faster fire propagation, a shorter time to flash over, rapid changes in fire dynamics, shorter escape times, shorter times to collapse, increased exposure problems, and other new and unknown problems. Stages of fire development in a single-family dwelling. When we look at this chart, we see that ignition starts early on in the process, and you'll have a growth phase that is only limited by the amount of fuel that is burning. As we get to the first gray area, we see that our growth is becoming limited by the amount of oxygen that's available, and then we will enter our early decay stage because we run out of oxygen. Then there'll be a change in your ventilation profile, which is indicated by the first red dot. When that happens, fire department may be forcing the front door to make fire attack, maybe a police officer is opening a door, maybe a resident or a neighbor is opening a door. When this happens, it mixes with that fuel-rich environment, and you have a rapid growth phase that is followed by a flashover that will continue to grow until it balances out with the amount of air coming in and the amount of heat and gases going out through that opening, and it sort of plateaus until our next change in the ventilation profile, which becomes our third red dot, which is the rooftop ventilation. After that, we're allowed to get more air in. We're also allowing more to escape out the top. We'll have another growth phase, and then we see through the fourth dot, which becomes our suppression activities, which really takes all the energy out of the equation. It's important for us to realize that fire growth in a single-family home is usually going to be ventilation limited, and that ventilating the fire without suppression could result in rapid fire growth. Fuel and construction combinations for the modern fire environment. These are going to produce much newer fire dynamics. Fires may grow rapidly and then enter a stage of dormancy due to insufficient levels of oxygen for the fuels that are involved. This may occur before a fire has even had an opportunity to reach a flashover state. The results of this will be a ventilation-limited fire, which is a fire that cannot grow into a fully developed or free-burning fire as the environment has become too fuel-rich and too oxygen-lean. Ventilation-limited fires. These fires result in an environment that waits for the introduction of fresh air that creates rapid and hostile fire growth. Making entry through the front door in these instances can introduce enough air into the fire area to produce rapid fire growth and flashover. Firefighters need to be aware that any opening in the structure constitutes ventilation. This has not been traditionally taught in most instances. Repeated experiments have produced violent flashovers shortly after the front door has been opened. Because of the extremely fuel-rich environment found on today's fireground, ventilation that is not preceded by, concurrent with, or immediately followed by effective suppression will introduce enough oxygen to rapidly bring the fire area to flashover. Table 1 shows the conclusion for residential fire behavior that were drawn from the experiments conducted on Governor's Island with NIST, UL, and the FDNY. Increasing the airflow to a ventilation-limited structure fire by opening doors, windows, or roof openings will increase the hazard from the fire for both the building occupants and firefighters. Increasing the airflow to a ventilation-limited structure may lead to rapid transition to flashover. There is a need for coordinated fire attack to coordinate the activities of size-up, entry, ventilation, search and rescue, and the application of water. Ventilation and fire flow paths. How fire spreads. In order to most effectively extinguish fires, we need to understand how they spread. All firefighters have learned about fire spread based on the principles of conduction, convection, and radiation, along with the classic fire triangle, which is still helpful to understand fire growth and the suppression of fires. Content fires generate large volumes of smoke, particulates, and gases, all of which are considered fuel. If this fuel is hot enough, it will ignite with the introduction of an adequate oxygen supply. In addition to these principles of fire spread, we need to add another factor that has not gotten the attention it deserves. Fire spread is largely a pressure-driven phenomenon. Fires spread along a flow path. A flow path is the lower pressure space between an inlet for fresh air, such as an open door or window, the fire, and the higher pressure space between the fire and the outlet for hot gases and smoke, such as an open window or roof opening. In a fire where only the front door is open, the fire will create a flow path of hot gases exiting through the top part of the door, while the bottom half of the door will allow for the introduction of cool, oxygen-rich air into the fire. This type of opening produces a two-way or bi-directional flow path through the front door. Some fire flow paths move in a single direction. Single-direction flow paths either supply oxygen by creating an inlet path or release the hot gases by creating an exhaust flow path. Single-direction flow paths can occur when there are multiple openings, such as an open front door and an open window, to carry gases in a single direction. Fresh air enters through the front door and hot gases and smoke exit through the open window. The hot gases are pushed along the flow path. If the flow path moves through the building before exiting to the outside and adequate oxygen mixes with the hot gas, the entire flow path can become a rapidly moving wall of hot gases or flame. Even a fully encapsulated firefighter cannot survive these conditions for more than a few seconds. Fire growth and development are impacted by both the amount of air entering the fire area and by the amount of fire gases exiting the fire area. Opening a door or window provides oxygen to a ventilation-limited fire. Providing an opening in a roof creates an exit flow path for the hot fuel and will accelerate the airflow into the fire as well as the spread of the fire along the flow path. This significant increase in oxygen combining with the hot, fuel-rich environment of a ventilation-limited fire can result in explosive fire growth. A ventilation fire sequence in which the main picture in each panel shows a room where the fire was started, with a small picture on the lower right showing the front of the building at the time. The graph to the right shows the position of the fire on the growth curve. We have the ignition phase of the fire with the front door being closed, followed by an immediate growth curve of the fire. This is shown from the hallway. The fire will reach its initial peak early on in the event. Shortly after, it will go into its first decay phase due to a lack of oxygen. Now, as the front door is reopened, the fire will go into its secondary growth curve. Within 5 seconds, the fire is reignited at the front door. A minute after the front door is open, the room is fully involved in a flashover once again. Controlling the flow path. Limiting the oxygen available to the fire until suppression actions can take place can keep the fire smaller and limit the heat release rate. Since opening the front door is considered ventilation, this action should be delayed until suppression crews are ready to or have already cooled the area. Careful coordination between suppression and ventilation is critical to a safe and effective outcome. Leaving the front door closed as long as possible aids significantly in controlling the fire by limiting the amount of oxygen supplied to the fire, as does stationing a firefighter at the front door to keep the door partly closed as the hose line is advancing to the fire. The conclusions that were drawn regarding the fire flow path from the fire experiments conducted at Governor's Island by NIST, UL, and FDNY are shown on Table 2. Improving the inlet and/or exhaust paths from the seat of the fire will result in fire growth and spread. Interrupting the fire flow path by limiting or controlling the inlet or controlling the outlet can limit fire growth. Controlling the door, keeping doors closed, allows less oxygen into the fire and equals lower temperatures. Anyone in the exhaust portions of the flow path between the fire and the direction of its travel is in a highly hazardous location. Controlling the flow path improves victim survivability. Our primary means of suppressing fires is to apply water. The research conducted by NIST and UL provide valuable knowledge about more effective means of applying water to a fire. It has been widely accepted that attacking the fire from the outside may push the fire through other parts of the building. Traditionally, it has been taught that a residential fire should be attacked through the front door or from the unburned side. It has often led to the assumption that offensive fire attacks must be made exclusively from the inside of the structure and that the fire must always be approached from the unburned side, effectively pushing the fire away from the unburned portion of the building and from any occupants that might be behind the advancing hose team. This technique requires firefighters to enter a burning building, often with low visibility and little idea of where the fire is located. NIST and UL research demonstrate that these assumptions are not true. The experiment showed that an offensive exterior attack, introducing water from the outside, reduced temperatures in other parts of the house at some distance from the fire area, but did not completely extinguish the fire. It slowed the growth of the fire by cooling huge quantities of very hot gaseous fuel and solid fuel below its ignition temperature. This offensive exterior attack is sometimes referred to as a blitz attack, a transitional attack, or by the military metaphor, softening the target. A transitional attack should be considered an offensive exterior attack. The purpose of this is to reduce fire spread, limit the heat release rate, and reduce temperatures to a safer level. It will also reduce the potential for a flashover. Used in sequence prior to the entry of lines into a building, if indicated, hit visible fire from the outside, then enter the structure for extinguishment and other operations. Table 3 shows the results of the exterior fire attack study conducted on Governor's Island. An offensive exterior fire attack through a window or door, even if it is the only exterior vent, will not push fire. Water application is most effective if a straight stream is aimed through the smoke into the ceiling of a fire compartment. Water should be flowed for about 10 to 20 seconds. This technique allows heated gases to continue to vent from the fire compartment while cooling the hot fuel inside. Fog patterns should not be used in this application. The fog pattern entrains large volumes of air and pushes air into the building. A fog stream can also block a ventilation opening, effectively changing the fire flow path. Applying a hose stream through a window or door into a room involved in fire resulted in improved conditions throughout the structure. Even in cases where the front and rear doors were open and the window had been vented, the application of water through one of the vents improved conditions throughout the structure. Applying water directly into the compartment as soon as possible resulted in the most effective means of suppressing the fire. Transitional attack is an offensive exterior fire attack that occurs just prior to entry, search, and tactical ventilation. This technique is also known as a blitz attack, a transitional attack, softening the target, or resetting the fire. A transitional attack should begin from the outside, but it is necessary to finish it from the inside. Coordinate the fire attack with vertical ventilation. Do not ventilate before an attack stream is ready. Table 4 shows the impact on building occupants with an exterior fire attack. Suppressing the fire from the exterior as soon as possible improves potential survival time. Additional ventilation that is not immediately followed by effective fire suppression reduced potential survival time. Being in the exhaust flow path of a fire resulted in reduced potential survival time. Controlling the flow path improves victim survivability. Controlling the door to a room when performing vent, enter, isolate, search improves the safety of the firefighters and the building occupants. Compartmentation, being behind a closed interior door prior to fire department arrival, provided increased protection compared to being in a room or area connected to the fire. Greater distance from the fire improves chances of survival. This image shows the results of one of the experiments conducted on Governor's Island with exterior water application. Water was flown into the structure at some distance from the front door at 180 gallons per minute for 28 seconds, resulting in 84 gallons of water being put inside the structure. Temperatures throughout the structure were reduced with this application of water. The temperature at the bottom of the stairs dropped from 1800 degrees Fahrenheit to 800 degrees. The living room dropped from 1200 to 300 degrees Fahrenheit. The back of the living room 700 to 300 degrees Fahrenheit. The top of the stairs were reduced from 900 to 500 degrees Fahrenheit. The image above shows firefighters positioning a hose line for an exterior attack on the second floor. Notice a straight stream is being used at a steep angle to allow water to enter the area to cool the environment. Other points to remember are this: you cannot push fire with water. Air entrained by a stream will cause heat to flow through a flow path. You need to reduce the amount of air introduced with the stream of water and let the hot gases flow out just as you are applying the water through the opening. Just like any other tactic, there is a correct way to flow water into an opening, such as a window or a door, if you do not want heat to follow the flow path. It is not possible to make statements about the effectiveness of ventilation unless one includes timing. Ventilation does not always lead to cooling. Well-timed and coordinated ventilation leads to improved conditions. Effective firefighting depends on a coordinated fire attack. Coordinating entry with ventilation, isolation, suppression, and rescue is of paramount importance. The same research that increased our understanding of fire flow paths, the effects of ventilation in ventilation-limited fires, and the use of a transitional attack also increases our knowledge of rescue techniques. Anytime you can close a door between the fire and other parts of the building, you increase the chance of survival for any trapped firefighters or building occupants. Isolating a room from the fire can provide a safe environment for a longer period of time. The rescue technique of vent, enter, search, requiring a firefighter to ventilate a bedroom window from the outside, enter the bedroom through the open window, and search for victims, is a technique that creates a dangerous situation for firefighters and for any victims in the room. By opening the bedroom window, you can provide a low-pressure vent for the fire to move toward. Recent experiments have demonstrated that this rescue technique is much safer if the interior door is closed prior to conducting a search. This isolates the room from the fire flow path. This modified VES process becomes vent, enter, isolate, and search. Some important points to remember regarding rescue and safety considerations are: if you add air to the fire and do not apply water in the appropriate time frame, the fire gets larger and safety decreases. Coordination of the fire attack crew is essential for a positive outcome in today's fire environment. The greatest probability of finding a victim is often behind a closed door. During a vent, enter, isolate, search operation, primary importance should be given to isolating the room being searched by closing the door to the room. This eliminates the impact of the open vent and increases tenability for potential occupants and firefighters, whilst the smoke ventilates from the now isolated room. If you get into trouble and need to escape, closing a door between you and the fire will buy you valuable time. Floor sag is a poor indicator of floor collapse. It may be very difficult to determine the amount of deflection while moving through a structure. Sounding the floor for stability is not reliable and therefore should be combined with other tactics to increase safety. Basement fires present unique hazards due to building construction methods and materials. Void spaces and unfinished raw materials are often present. This can lead to quick failure of structural components as a primary hazard. Attack straight downstairs may not be a safe option since it places personnel on the outlet side of a unidirectional flow path in most situations. The traditional tactic of pushing down interior basement stairs to the seat of the fire should no longer be considered a safe option. One of the findings of recent research on basement fires was that water applied via interior basement stairs had limited effect on cooling the basement or extinguishing the fire. However, water applied through an external window or door quickly darkened down the fire and reduced the temperatures throughout the building, and no fire or hot gases were pushed up the interior stairs. Some key points to remember from the basement fire experiments. Thermal imagers may help indicate there is a basement fire, but cannot be used to assess structural integrity from above. Attacking a basement fire from a stairway places a firefighter in a high-risk location due to being in a flow path of hot gases flowing up the stairs and working over the fire in a floor system that has potential to collapse due to exposure. Coordinating ventilation is extremely important. Ventilating the basement creates a flow path up the stairs and out the front door of the structure, almost doubling the speed of hot gases and increasing the temperature of the gases to the level that could cause injury or death to a fully protected firefighter. Fire flows from the basement developed in locations other than the stairs, as the floor assembly often failed close to the location where the fire started. Flowing water at the top of the interior stairs had limited impact on basement fires. Offensive exterior attack through basement windows was effective in cooling the fire compartment. Offensive fire attack through an exterior door was effective in cooling the fire compartment. Thank you for participating in this continuing education class on evidence-based practices for